So let's start with Theorem 103.1, and this is part of what we call cancellation of the succession operation. So next can get cancelled in an inequality. So suppose n and m are natural numbers, then this is saying if you have next n less than next m, then you can cancel the nexting and still have the inequality being preserved. This is pretty plausible, right? It's sort of saying if one dot is to the left of another dot, and then you move the entire picture one to the left, sort of removing the next, then it's still true that the left dot was to the left of the right dot. I don't know if that helps. But one interesting thing about this is that the proof is actually not by induction for once. Okay, how in the world can that happen? A proof about natural numbers that isn't using induction? It can happen because we've already used induction a lot to prove certain things. So we're currently here on Theorem 103, but we already used induction a whole bunch to prove stuff above, right? So we can use that stuff. Technically, when we're using that stuff, we're still using induction, just indirectly. It's just the induction, proofs by induction are hiding inside the results that we're using. So it's not going to be by induction, it's actually direct. I'm just going to straight up assume n and m are natural numbers, fixed, and next n is less than next m. And then I'll try to prove that n is less than m. And I said I'd use previous stuff, I'm actually going to use transitivity. So that's where the induction is hiding. Induction is going to be somewhere. Now, we have next n less than or equal to m, right? Because this less than and next, I can mush these together and turn it into a less than or equal to. So next n is less than or equal to m. And let me write it all together. We also have n is less than its own next. So since n is less than this, which is less than or equal to that, we have n is less than that. That's transitivity right there. So I guess that one is using Theorem 100 point something that involves a less than and a less than or equal to. So I guess this one, 0.3. And that's it. Now let's work on the second part of Theorem 103. So this is also about cancellation of the succession in an equality. So it's kind of saying if you have the nexts of two things being equal, then the two things are equal. If next were the symbol for a certain function, which it's not, but if it were, then this would be sort of saying that next is an injective function. But with the way we've set things up, we just haven't made it a function. But we will pretty soon define a function that carries out the what next carries out. Anyway, let's get into this. Again, this will not actually directly use induction. It's just going to use other things that themselves used induction. So just assume n and m are natural numbers and that their nexts are equal. And then we try to prove that n equals m. So we have n is less than next n, right? Which is equal to next m. So n is less than next m. What I'm using here, by the way, is, I used it before too, just this idea that things are less than their own next. And similarly, m is less than next n, next m, right? M is less than its own next, which is the same as this. So m is less than next n. So This, if I just mush the less than next together, using this principle again, this is n less than or equal to m. So this is m less than or equal to n. So we have n less than or equal to m less than or equal to n. We're trying to prove n equals m. So actually, n less than or equal to m, we will see that this is the same as n subset m, and m less than or equal to n is going to be the same as m subset n. This is not something that happens in general at all. Normally you would not do this, but for natural numbers, because of the weird sort of set theoretic way that we constructed them, you end up getting these. So it's interesting. So let's just prove. So consider, how about this? Claim n is a subset of m. And now it's really important that I not make that look too pointy. N is a subset of m. These should be pointy. Here's a proof of the claim. Consider any k in n. Then k is less than n, because less than is a fancy way of writing in, right? So k is actually less than n, which, by the way, is less than or equal to m. So by transitivity, by Theorem 100, part 3 again, actually, by this, we have k less than or equal to m. There's the induction. So I'm not doing induction here, but I'm saying that somehow induction was needed in order to get this to work, because I'm using Theorem 100, and Theorem 100 used induction. And let's see. That conclusion is correct, but it's weaker than the conclusion I want. I want k less than m. That is, k is in m, right? That's what less than means. So take any k in n, then it follows that it's in m. And then you also get the other inclusion. How about I just copy this and replace? Here. And there we go. And I think that finishes the proof, right? So n is equal to m because we have both inclusions. And that successor cancels. So if you have the nexts of two things being equal, then the two things are equal, assuming you're talking about natural numbers.